Welcome to Lecture 24, Section 5.1 of the text Elementary Linear Algebra by Ron Larson, 7th edition, Cengage Learning. Length and dot product in the n-dimensional vector space Rn. This is Dr. Gilbert, Eyabi. First, lecture goals. Number 1, find the length of a vector and find a unit vector. 2, find the distance between two vectors. 3, find a dot product and the angle between two vectors. Determine orthogonality. Verify the Cauchy-Schwarz inequality, the triangle inequality, and the Pythagorean theorem, and use a matrix product to represent a dot product. Let's start with the definition of the length of a vector in Rn. Let V be the vector defined by the components v1, v2, right up to vn. Then the length of V has this following symbol and is defined as the square root of the square of the first component plus the square of the second component plus the square of the nth component. That is how we define the length or the norm of a vector in Rn. Example, consider the vector V defined by the entries 0, -2, 1, 4, -2. Then the length of V or the norm of V is the square root of 0 squared plus -2 squared plus 1 squared plus 4 squared plus -2 squared, which would give us square root of 25, and that is 5. We take the positive square root because length cannot be negative. Now I want you to verify that if V is defined by these components, then the norm of V equals 1. You can quickly see that if I take the square root of 2 over root 17 all squared, I would end up with 4 over 17. Same thing here, 4 over 17, 9 over 17. So I end up with the square root of 17 on 17, which is 1. This is called a unit vector. If the norm of V equals 1, then V is a unit vector. Theorem, length of a scalar multiple. Let V be a vector in Rn and let C be a scalar, a real number. Then the norm of C times V equals the absolute value of C times the norm of V. Interesting. Theorem, unit vector in the direction of V. Let V be a non-zero vector in Rn. Now define another vector U by V divided by the norm of V. Then the vector U has length 1 and has the same direction as V. Of course, if you take the norm of U, that will be the norm of everything on the right hand side, which will be the norm of V divided by the norm of V, and that equals 1. So given any vector V, I can actually find a unit vector that has the same direction as V. And how do I generate such a unit vector? The vector is simply my U, which equals V divided by the norm of V. Example, find the unit vector in the same direction as the vector V defined by the three components 3, -1, 2. And actually verify that this vector is a unit vector. It has length 1. So set my U to be the vector V divided by the norm of V, which will be 3, -1, 2 divided by the square root of 3 squared plus -1 squared plus 2 squared, And all of that will give me 1 over square root of 14 times 3, negative 1, 2. And this new vector here is my unit vector that is in the same direction as the original vector 3, negative 1, 2. So whenever you're given a vector and asked to find a unit vector in the same direction, it is simply that vector v divided by the norm of v. Now observe that the length of this new vector is simply going to be 1. And that is why it is called a unit vector. Now what about the distance between two vectors? Let u and v be vectors in Rn. Then the distance between u and v is the norm of u minus v. The length of u minus v. So we're looking at the square root of u1 minus v1, all of that squared, plus u2 minus v2, all of that squared, plus un minus vn, all of that squared. Observation: the distance between u and v is bigger than or equal to 0. The distance between u and v equals 0 if and only if u equals v. And the distance between u and v is the same as the distance between v and u. Okay, now let's define the dot product of two vectors in Rn. Let u be the vector defined by the entries u1, u2 right up to un, and v the vector defined by the entries v1, v2 right up to vn. Then the dot product of u and v, denoted by u dot v, is actually a scalar quantity, and it is defined as u dot v equals u1 times v1 plus u2 times v2 plus un times vn. We call this the dot product of two vectors in Rn. For example, in R4 we have the vector u and the vector v, and the dot product of u and v would be 1 times 3 plus 2 times negative 2 plus 0 times 4 plus negative 3 times 2, and that equals negative 7. Theorem: properties of the dot product. Let u, v, and omega be vectors in Rn and C a scalar. Then the following properties are true. Number 1, there is commutativity in Rn with respect to dot product u dot v equals v dot u. Secondly, there is distributivity with respect to dot product. And for scalar multiplication, c times u dot v equals cu times v, which is the same as u times cv. Number 4, the dot product of v and v is simply the square of the norm of v. So we can also say that the norm of v equals the square root of v times v. And lastly, v dot v is bigger than or equal to 0. And v dot v equals 0 if and only if v equals 0. Another theorem, the Cauchy-Schwarz inequality. It's an interesting inequality. It puts together absolute values and norms. And what it simply says is that if u and v are vectors in Rn, then the absolute value of the dot product of u and v is less than or equal to the product of the norms of v and u. So the absolute value of u dot v is less than or equal to the norm of u times the norm of v. And the angle theta between two vectors u and v is defined as follows. Cos theta equals the dot product of u and v divided by the norm of u times the norm of v, and theta is always between 0 and pi inclusive. Now let's introduce the idea of orthogonality between vectors. Two vectors u and v in the n-dimensional real space Rn are said to be orthogonal if their dot product equals 0. Very easy. Triangle inequality. The norm of u plus v is less than or equal to the norm of u plus the norm of v. We call that the triangle inequality. And the next is the Pythagorean theorem. Remember the Pythagorean theorem? C squared equals a squared plus b squared. Well, if u and v are vectors in Rn, then we say that u and v are orthogonal if and only if the square of the norm of u plus v equals the square of the norm of u plus the square of the norm of v. It's also a very simple theorem to prove, and I will leave that as a simple exercise for serious students. Now, the dot product and matrix multiplication. If u is this column matrix and v is this column matrix, the dot product of u and v is actually gotten by representing u dot v as u transpose times v, which makes it possible to actually compute the product of these two column matrices, and that would just be u1 times v1 plus u2 times v2 plus un times vn. For example, the dot product of the vectors u and v, this is a column vector, this is a column vector. To compose the dot product of these column vectors, we represent them as u transpose times v, which is 2 0 times 3 1, and our answer is 2 times 3 plus 0 times 1, which is a 6. Very beautiful concepts. Thank you very much.